Merhaba Hoca. I'm Nur Nufel. I'm going to solve the first question from the homework, and it says ANC feedback control system with the following open loop transfer function is provided here with this function. We need to draw the approximate Root-Lucas diagram. Okay, so to draw the Root-Lucas diagram, first thing we need to sorry. Okay, we need to find the zeros and poles. Here it's supposed to be zeros and here it's supposed to be poles, but here we don't have zeros. Or we have actually, but not here. And here. Okay, so the poles will be s equals to 0, S1. S2 equals to -2, S3 equals to -4, and we need to draw them on the Root-Lucas plane. Okay, here is the 0, here is the -2, here is the -4. Here's Jim again, here's this. Okay. Then the Root-Lucas, it's between two zeros, like from 0 to -2, and from -4 to the infinity. So here is Root-Lucas and here is Root-Lucas. So this is not. Okay, let's continue. We need to find the number of branches or the number of VS here. So it's 3. Then we need to need to find the asymptotus. The asymptotus is n minus m, which is 3. The number of poles minus the number of zeros, it's 3. We need to find the sigma, the intersection of it. It's the poles minus the sigma of zeros over n minus m, which is 3. Here, -6 over 3 equals -2. So the -2 here is the intersection. Okay, now we need to find the alpha, the theta. Theta will be 180 multiplied by 2k plus 1 over n minus m. N minus m, it's 3. K is first thing 0, then 1, then 2, then 3. So when it's 0 here, it's going to be 180 over 3. So minus and negative and positive of 60 degrees. The second one, k will be 1. So 2 multiplied by 1, 2, plus 1, 3, over 3. Here is 3. So this will go with this. So it's going to be 180. So 1, 2, 3. We need 3 thetas. So the intersection point is here. 3 thetas. 1 from here to there. 60 and -60. And 1 here. Then that's it. Yes. Now we need to find the breakaway and break-in points. How to find the breakaway and break-in points? Why? We need the characteristic equation. We need to find the characteristic. We need to find the characteristic equation. Okay. The characteristic equation. Okay, the characteristic equation is to the power of 3 plus s to the power of 2 plus a to the power of 6 plus k equals to 0. We need the k alone and take the derivative of these. When the k alone, let me change the k equals to minus s to the power of 3 plus 6 to the power of 2 plus 8s. And now we will take the derivative of k. The derivative of k is going to be dk over ds equals to minus 3s squared plus 12s plus 8. Now, we will not take the minus, then we will go to analyze this s. 3, 12, 8. The first one is s equals to minus 0 0.845, and the second one minus 3.154. But this one is not included into the root locus because the root locus is from 0 to -2 and from -4 to the infinity, so this is not involved. Okay, so this is the breakaway point. The breakaway point. This is one. Okay, so this is here, the breakaway point. Now we need to find the intersection between the j omega axis. Okay, so also we need the characteristic equation. It's going to be s to the squared, a triple, sorry, plus 6s squared plus 8s plus k equals to 0. S squared, s and s 0. Here it's 1, 8, 6, k, and here is k. We need to find the a. A equals to 6 multiplied by 8, 48, 48 minus k over 6. So the range of k here is k is bigger than 0. Okay, range of k, to find it, we need the 48 minus k, or 1 minute. We need the 48 minus k bigger than 0. This is bigger than 0. How? So the 6 will go there, it will be gone. So it's going to be 48 minus k is bigger than 0. And the k will go to the other side, but we will flip the signal, so it's going to be k smaller than 48. Okay, now we found k smaller than 48, but the second k, okay, we will take the second order s, and it's going to be 1 minute. Oh, one thing, if we want to find the k, we just have to put k in the main function, and k finally will be 3.08. Okay, so the range of k finally will be k bigger than 3.08 but smaller than 48. This is the range of k. Now we need to find the intersection between j omega poles. Let me write it here. S squared, 6s squared, plus k equals to 0. So the first poles will be 2 multiplied by root j. Okay, so here S1 and S2 minus and positive 2 root 2 j. Now let's put them. Here is 1, here is 2, here is minus 1, here is minus 2, here is minus 2 to the root. Okay, now we just need to draw it. From the breakaway point to the intersection, just like this. Yeah. Just like this. Okay, that's it. That is the root locus. Then here we need to see the second B. Comment on the time response under damped, critically damped, and over damped stability of K. Actually, when the K, from the range here that we found, when the K is smaller than 48 and bigger than 3.38, it becomes critically damped. But the system is it's stable. That's it. Now we put the simulation. Okay. Bismillah. Here's the root locus. It's loading. Still loading. Reload. Yes. The same as the okay. Pretty much typical. Yes. That's it for the first question. Merhaba hocam. This is the second question from the homework, which says there are three op-amps connected to the cascade in a control system. The waveform are as shown in the side from here and here. Sorry. Okay. Find the parameters value used if the op-amp used in the circuit are connected in parallel and pass. Okay, this is the second. Okay, let me draw an appropriate connection to find the parameters. So here we have the first op-amp, the second op-amp, and the third op-amp. From here, let's go down and draw them correctly, rightly. So the first op-amp, from the waveform here, we know it's an inverting op-amp. Why? I will tell you why. Okay, it's an inverting op-amp, so it's going to be just like this. And here we have a resistor, and we need to find the value of the resistor. Here is V1 and here is Vn. The function will be RF over Rn equals to the gain, which is V1 over Vn. From the wave here, we know that the V out or V1 equals to 0.5 and minus. So from this, we can find the value of the RF and Rn. So the RF equals to 5 kilo ohms, okay, and the Rn equals to 10 kilo ohms. So yes, there is minus here. Okay, this is for the first op-amp. Here's RF and here's RN. It's an inverting op-amp. Okay, for the second op-amp, it's an integrator op-amp. How did I know it's an integrator op-amp? Because the ramp waveform here, I know it's an integrator op-amp. So let me draw it. Okay, I'm sorry. Okay, here is also an inverting op-amp. Okay, and here we will have a capacitor. Here is V2. Here we have an resistor, and here is V1 coming from this op-amp. Then here we have a capacitor. Let's say C, and here R. So we need to find the value of C and R from the wave form. We already know it's an integrator, so an integrator will be R1 over RCS. Okay, V1 over V2. From this information, I will know that it will be minus the gain, يعني the gain G2S will be minus 2 over S. Okay? And the gain in the first op-amp, I forgot to write it, it's going to be minus 0.5. Okay, 0.5. And the values of the capacitor and the R here, the R will be 100 ohms, and the capacitor will be 5 micro farads. Okay, so now I found the first and the second gain. Let's find the third one. The third one will be an inverting amplifier, also as same as the first one. Here is coming V2, I think, and here is a resistor. Here is also a resistor, and here we have a op-amp, an inverting op-amp. Okay, here RF, RN. Okay, RF here is 5 kilo ohms, and here is an inverting op-amp, so it's going to be done. Sorry. Okay, an inverting op-amp. Then, how to find the gain of this op-amp, as same as the first one. So the gain here will be minus 0.25, because this is Rn here equals to 20 kilo ohms. So 5 over 20, K goes with a K, and here's a minus because it's RF over Rn, okay, equals to minus 2. Okay, now to find the final transfer function, it will be the total of all the functions together. So, equals to the 0, okay, plus the first one, which is also a minus, so, okay, minus S over 2 over S. I'm sorry. Okay, that's it. Now, how did I choose the parameters of the capacitor and the resistors from the waveform? Okay, I didn't choose it from the waveform, but it's to match the given in the waveform here. Okay, now so obtain the transfer function. Okay. How to draw the amplifiers? It's just going to be here an op-amp, and here an op-amp, and here is the final op-amp, and the gain is 1. How did I know the gain is 1? From also the waveform here, the gain is 1. Okay. And they are all connected together. Like here is the first op-amp, here is the second op-amp, and here third op. Okay. When the three operational amplifiers are connected parallel, their outputs are summed using a collector with a unity gain. The overall transfer function becomes the sum of the individual transfer function. Okay, the resulting system contains a proportional and integral terms. So the circuit represents a PI controller. I don't know really well what this PI controller. Okay. Now, يعني after drawing the three op-amps, or after drawing the circuit that identified the first op-amp as an inverting amplifier, the second op-amp as an integrator amplifier, and the third op-amp as a gain stage. So in the parallel configuration, the circuit behaves as a PI controller. Okay, now let's see the third, which is related to MATLAB. Implement the system MATLAB Simulink and show the graphs. The same graphs I noticed here in MATLAB. Okay, here's the code, and here's the figures. The same, the Vn is 1, the V1 is minus 0.5 here, and the output is from 0 to 4, and here is the integrator amplifier, and here is the also the final one. Moment. No. Why? And here is the is. Let's run it again. Let it run again to see the final result. It wasn't like this. Okay, that's it for the homework. Thank you, teacher. Merhaba Hoca, I'm going to solve the third question of the homework. The third question says, the open loop transfer function and unity feedback control system is given below. This is the function. First thing, specify the type of the system. So by looking at the system is type 1. Why? Because, I'm sorry. Because here I have s to the power of 1. Okay, and here we don't have anything. So it is type 1. Okay. Then calculate the continuous state error for unit digit input ESS. And the steady state error for this one, okay. First thing we need 10 over S multiplied by S plus what? Plus 5. Okay, to find the steady state error, first thing we need to know what is steady state error. First thing, ES equals to RS, which is the input unit input. Okay, 1 plus, let's say GS. This is GS. Then we need to find the steady state error equals to the limit when S goes to 0 multiplied by S multiplied by ES. Okay, now to find this, we know already it's the first type. So in the first type, the step input, it's going to be 0. Why 0? Because here it's S Okay, here is the, okay, let me write it again. Limit s to 0, s multiplied by 1 over s. So, okay, multiplied by 1 over, sorry, 1 over 1 plus 10 over s, then s plus 5. This will go up there. So it will be s plus 5 over s plus 5 plus 10. If we put the limit here, I'm sorry, it's going to be 0. Or in another way, the ESS will be 1 over KP position. What is not P? P? No, it's going to be 0. Okay, it's going to be 0. Okay, this is for the first one. For the second one, the second question, it says calculate the continuous, okay, the third one, if the unit ramp input is applied for a system, find the steady state error. To find the steady state error for the ramp, it's going to be a certain number, not 0 or infinity. Why? First thing, because it's the second order, and when we say ESS, okay, ESS equals to limit s goes to 0, s multiplied by 1, s, this will go by 1, 1 plus 10 over s, s plus. Okay, how we're going to solve this? Much easier way. Here we have a constant called kv for velocity. The steady state error will be 1 over kv. Okay? Okay. So first thing, we need to find the kv. Kv equals to s multiplied by gs. Okay? For the limit 0. Don't forget. When s multiplied by gs, so the s here multiplied by 1 over s multiplied by s plus 5, the s here will go with here, and it's here 10. So here it's going to be 10 over 5, and it's going to be 2. So the steady state error will be ESS will be 1 over 2, which is half, 0.5. So this is the steady state error. Now, comparison with standard, okay, the closed loop transfer function. Okay. Okay, comparing the standard. Okay, first thing we need to find the closed loop transfer function. Okay, it says 10 over s multiplied by s plus 5. Yani 10 over s squared plus 5s. Okay, we need to find the closed loop. So it's going to be 10 over s squared plus 5s over 1 plus 10 s squared plus 5 squared. I'm sorry, s squared plus 5s. Finally, it's going to be 10 over s squared plus 5s plus 10. And here is the characteristic equation. This is equals to omega n squared over s squared multiplied to zeta omega n multiplied by omega n squared. From this equation here, we found that the omega n equals to root of 10. Okay, and zeta, how we will find zeta? 2j the root of 10 equals to 5 from the equation here, like this is equal to this. So j here will equal, not j, I'm sorry, zeta. I don't know why I'm writing it like j, it is zeta. zeta, okay, 0.79. Then what else we need to find? Okay, found the frequency of the system, found the zeta. That's it. Let's also find the maximum overshoot and rise time and settling time. It's easy. The maximum overshoot percentage equals to e to the power of minus pi, okay, minus by pi zeta over root 1 minus zeta squares. So the e multiplied by 100. Don't forget it. Zeta is 0.7 when we calculate it. Okay, it is 1.73 percentage. I'm sorry, I forgot. %1.73. Then we need to find what else? Settling time. The settling time, okay, will be 4 over omega zeta. Why 4? It is for 2 seconds. If it's 5 seconds, will be 3 over. So it's going to be 4 over root of 10 multiplied 0.79 equals to 1.6 seconds. Okay, and rise time. The rise time equals to 1.8 over omega n 1.8 over the root of 10 equals to 0.57 seconds. Okay, now let's do the simulation on MATLAB. This one. Okay, let's run it. Yep, here is the zeta, as I said, it is 0.79, the omega n root of 10, the rise time, no, it's settling time, 1.6, the rise